thank you for joining us. Today, I'd like to introduce the Keil Functional Safety Runtime System, and in particular have a look at the safety version of their RTX RTOS. The Functional Safety Runtime System is a collection of components that are available in the microcontroller development kit for ARM, but these provide the same functionality, but are safety certified for use in safety systems. The RTOS is safety certified, but also provides a number of enhanced features over the standard RTOS that allow us to create functional isolation within safety systems. So again, this is an interesting concept because it minimizes the effort that we need to certify our overall application through clever use of software. So again, that's really what we want to go through today. Before we start, it's also important to realize that the functional safety runtime system is designed to work with the Keil tools and the ARM compiler, and has been certified with the safety version of the ARM version 6 C compiler. So again, to use this system, you would also need the MDK Pro version, which includes the safety certified compiler. So this is a compiler that's under a long-term maintenance branch. It's a special development branch, and the compiler has also been certified to produce code at all its different optimization levels. So it gives you the full flexibility of the compiler as well. The overall functional safety runtime system has been certified to cover a number of industries. So again, road vehicles, industrial safety, railway systems, and medical devices. So it covers a very wide range of applications for safety systems. If you're interested in other safety standards, please let us know. We can discuss this with Keil. So the idea of functional isolation is that we can create our application, and we can divide it into different components within the application, so that we can have components that are performing the safety function. So this may be a main control loop that's controlling elements of our equipment. And in addition, we have some other components which are not involved in the safety application. So these are typically things like networking, user interface, or other non-safety application. And we can term these components as interference-free components. So this means that they are part of the system, but they're not safety critical or safety relevant. Okay, so they don't provide any code to the safety system at all. However, they may interface with the safety subsystems. Typically, for example, you might have a web server that's showing the status of the system, so it needs to monitor some of the data that's involved with the safety application. So what we want to look at is a way of separating our interference-free components from our safety components. And we can do this really by two kind of key methods. This is spatial isolation. So this is the ability to control access of the code that's executing to the specific microcontroller resources. So we can define regions of flash, of RAM, and peripherals that a particular component is allowed to access, and prevent it from touching any other parts of the system, and also being able to formally guarantee that that's happening as well. And secondly, we also want to be able to prove temporal isolation. So this is the ability to monitor the timing constraints and runtime of different components within the system, and guarantee that they're meeting those runtimes. So this also means that we have more error cases in our system that can be detected. So we can have a more sophisticated control and recovery system. So if a non-safety component fails, for example, we can stop it and try restarting it. If there's a problem with a safety component, we can detect it and place the system into a safe operating mode. So again, we've got much finer control over what happens to the system in the event of an emergency. So the Keil RTX RTOS is an open source real-time operating system that's provided within the MDK, but it's also available for use under a 3-clause BSD license. So this provides a lightweight real-time operating system for Cortex-M microcontrollers. Within the functional safety version, we have an extended commercial version of that operating system that provides a number of features that allow us to construct our code for spatial and temporal isolation. Alongside the RTOS, there's also a new CMSIS standard called CMSIS Zone that helps configure our application to support functional isolation. So this is again a free application that you can download and use within your own systems, whether you're using the Keil tools or GCC or other compilers. And again, we'll have a look at CMSIS Zone as we go along as well. So within the RTOS, there are a number of features that we can use to create functional isolation systems. On the standard version, we have control over whether the background code is executing in privileged or unprivileged mode. So that's reducing its access to standard registers within the Cortex processor. We can also statically allocate all of the resources that we're granting to the operating system threads. So this means that we're taking a much more rigid approach to laying out memory. We will discuss this a little bit as well. Within the commercial safety version, the functional safety RTX, we can also create a memory protection unit protection zone. So this is using the MPU that's within most of the Cortex processors to effectively monitor zero overhead what resources each of our threads is accessing, and it will throw up an error if we go outside any allocated resource for that thread. We can extend that with safety classes to make sure that we're not misusing RTOS objects like mail queues and event flags, which would allow us to bypass some of the memory protection zone. But again, we'll discuss this in a little bit. For temporal isolation, each of our threads can now have a software watchdog so that we can monitor the runtime of a thread and guarantee it doesn't exceed a maximum runtime. And again, as I mentioned earlier, we have more fault handling features which we can use to control the overriding application. So if you're familiar with RTX, this is our configuration, central configuration file where we can set up the application. So in here, there's some new tick boxes to support the different safety features. But also in the top left-hand corner, when we're using the standard version of RTX, we can just normally give it a chunk of memory, which it uses for resources for each object that as it's created, so threads and semaphores, etc. When we're using the safety version, we are going to statically allocate all of the resources that are used by our threads. So we would reduce this memory pool down to 0 because we're going to do all the legwork ourselves and manage all of the memory allocation. So this is a bigger overhead, but it allows us to rigidly define our memory map. Also on the bottom right-hand corner, we can control the type of processor access that our background threads have. So here we would normally allow them to have privilege mode, so it allows us to touch everything that's within the processor and the memory map. But here we can switch this to unprivileged mode, and this restricts what the code within our background threads can do. So they can't talk to the processor system control block, so they can't enable and disable interrupts. They can't change the SysTick type and other critical registers in the chip. So we're leaving that up to privileged code within the RTOS kernel. And we can extend this across the whole of the memory map with the use of the memory protection unit. So then we can change the access privileges to different areas of RAM and peripherals and flash. So we can build a more complex memory map to work within. So the way that that's working when we're running in thread mode, we'll now be running it as unprivileged code. So we can talk to peripherals, we can use RAM, but we can't talk to critical registers within the processor. In order to do that, or access the kernel functions, when we make an OS call, rather than doing a branch to the code, we're actually invoking a supervisor call. So this generates an exception and places us into the handler mode that then gives us access to the kernel functions, which run with full privileged access across the chip. So by configuring the RTOS in this way, we're sort of creating a privileged system level of the chip, and then we're creating a background unprivileged level where our application code is running. As we'll see a bit later, we can also create our own functions that will sit in the privileged level and are invoked by supervisor calls. So critical functions such as enabling, disabling interrupts can be housed at the system level of the chip. And we can also then control what functions, threads can access those functions. So again, we can lock down how our code is operating a bit more. So within all of the ARMv7 and ARMv8 Cortex processors, so basically that's everything except the Cortex-M0, there's an optional unit that can be fitted called the memory protection unit. So this provides up to 8 regions where we can define the type of access to a selected area of memory, be that flash, RAM, or peripherals. So we can grant execution or read-write access, or privileged and unprivileged access. So again, we can split the chip up, and as our code runs, if it accesses a region that it's not allowed to, an exception will be generated. Now, within the functional safety version of RTX, we use the memory protection unit to create a set of memory protection zones. So as each thread is executing, the memory protection unit is programmed to grant it the resources that it requires. So it would be given RAM, it would be given its peripherals and its flash, so that as it executes, if it goes outside of its protection zone, an exception will be raised. When we switch to another thread, we have a callback function that allows us to reprogram the memory protection unit to set up a new zone for the thread that starts running. So effectively what we're doing as our code is executing, each thread is kind of sandboxed and allowed to execute within its own resources, and we prevent it from accessing any other resources on the chip. So this way we're spatially isolating every thread and granting it its own resources. Plus we can also have some shared resources for passing data, so mail queues, etc. So for example, in a typical example application where we're controlling some traffic lights, we can have a number of threads. So a normal operation, which is our main application control loop, along with its low-level driver, an ADC, which is simulating a road traffic. We can have other threads which validate the operational data. And then we can have our interference-free thread, which is our communication thread that's providing a web server to remotely monitor the activity of the traffic light. We can also integrate software test libraries. So this is a library that will validate the RAM, the flash, and also the performance of the CPU during runtime. So this is granted its own thread, and it sort of runs in the background just to check and guarantee that the hardware is still operating correctly. We can also create a safe mode thread so that if the operation of the traffic light fails, we can fall back to our safe mode where we can just flash the orange light on the traffic light to let drivers know that there's a problem. Now, in order to set this up, we normally just create our threads and allow the kernel to allocate the memory. But within a safety application, we have a lot more of that low-level legwork to do. So we have to statically allocate all of the thread code within the application code. We have to position that with the linker script file. Then we have to set up the MPU tables to define the MPU regions for each thread as the code's executing. And that will then be called by an RTOS callback function to switch the MPU table as a new thread becomes active. So we first of all need to take a standard page of memory that's within our microcontroller and then subdivide that into memory regions that are going to be allocated for each of our threads. We also need to provide regions for some of the standard blocks of code that will be within our application. So things like the kernel data, the certified C library. There's also the debug agent, the event recorder, which will be shared across all of the threads. And that is very useful for reporting runtime information back to the debugger. And then there are other standard features that are created by the RTOS, so a timer thread and also the background idle thread as well. So we have to take all of these into account. And then within our linker script file, we provide memory regions to reflect that layout. And then we have to allocate the C modules that contain the relevant code into those regions. So here we have the region for the background control loop, and then we're picking up the compiled module and allocating it into that region. So we have quite a large linker script file. It's very straightforward, but we have to create it and manage it, which, as I say, is a bit more legwork. So this will allow us to rigidly lay out the memory, and then within each of our application code, we have to statically allocate the thread memory. So rather than just creating a thread, so at the top here, we define an array, which is going to be used as the thread stack. In the attribute that's used when we create the thread, we have to define that array as our stack space, and then we create the thread and we have our statically allocated region for that thread. Once we've done all of that, we also within the thread attribute need to create a thread zone. So this is going to be our protection zone number. So we've laid out the memory and now we're allocating the zone number. So as the kernel runs, it knows what thread's executing and what zone needs to be activated. So this is encoded into the attribute bits that are part of the attribute structure. And then once we've done all that, we've defined our thread, we've laid out its memory, and we've defined its protection zone. We then need to create an MPU table that reflects that memory layout. So here we're programming up memory protection regions to grant access to the flash, RAM, and peripherals. So when we switch to that thread, we'll know what memory protection zone we're running in. Then the callback function in the kernel will activate the relevant table and program the MPU. The thread can then run within its resources. If it goes outside, it will generate a memory protection fault. And then our callback function, so every time we do a task switch, we get a callback which is past the active zone number. We can then disable the memory protection unit, load up the correct table, for the thread that's about to run, and then re-enable the memory protection unit. So now that thread will run within its own little environment, and we can guarantee that it's isolated from everything else. Similarly, if we're creating a number of critical functions, we can define these as supervisor calls. So these will run at the same level as the kernel, so that when we call, for example, to enable the Ethernet interrupt, it will be called via an exception, a supervisor call. We'll elevate up to the handler mode, run in full with full access to the chip. So now we can talk to the NVIC, enable the interrupt, and then quit out again afterwards. But also at this level, we've got the call OS thread get zone, where we can check what the calling zone number is. And this allows us to ensure that that particular thread with that particular zone is allowed to access this function. So again, there's a bit more nuance here, that we can limit our privileged important functions to certain threads and certain memory zones. So we have quite a bit of legwork to set up our memory layout and define our MPU tables. So there's a number of files that we need to configure, and that's quite easy to make mistakes, especially over the full life cycle of the project, and if there's any number of team members as well. So there is a new CMSIS standard called CMSIS Zone, which is designed to help manage complex memory maps. So typically this is useful for safety systems. It's also used within security, where we'll have, for example, secure world code and non-secure code. So these are two separate projects. Or if you have a multi-core system as well, where several processors are sharing resources. So a zone is a bit of a flexible concept. It's referring to a memory region, but it can generate a zone as a full project. So we can, for example, have two zones and they become two different microcontroller projects. Or in the case of a safety system that we're looking at now, we can have an execution zone where each zone is the resources for a given thread. So a zone is, as I say, a little bit slippery to begin with, but it falls down into those two key use cases. So while the CMSIS zone refers to templates and markup languages, the way that we use it as an end user is through a free-to-use utility called CMSIS Zone Utility. This is effectively an Eclipse plugin that allows you to graphically define and manage zones, and it really saves an awful lot of work. So here within Eclipse, we can start up with CMSIS Zone. When we create a project, we tell CMSIS Zone what microcontroller we're using, and then from the CMSIS pack system, it will import the memory map of that microcontroller. So it's flash, it's RAM, but also importantly, all of the peripherals as well. So there's no immense amount of work to set up and configure this. It's pretty much ready to go. So we'll have our default pages of RAM. We can then create our subdivision of those pages. So again, these are really the code that we're going to allocate to our different threads and different components that are in the code. And once we've subdivided those, we can create zones, which are different memory execution zones for all of our different threads. So here the green is where we've allocated memory to that zone only. The orange is for shared regions. So we've got RAM, shared RAM for passing data, and also for the event recorder to communicate up to the debugger as well. So as well as RAM and flash, we can also allocate peripherals to a given zone as well. So once we've defined our memory layout and our zones, we can then allocate the different modules, code modules, into a specific memory region. This is a little less intuitive, so this is done through the local properties of the memory region and in the info box shown there. And we can also control the type of access that we have within this zone as well. So read, write, privileged, non-privileged, etc. Once we've laid out all of our resources, defined our zones and allocated the code, we can then, on the final tab that's within CMSIS Zone Utility, decide what type of project this is. So as an execution project, when we do the code generation, it will create a memory layout header, it will create the linker scatter file for us, and also the MPU zone tables and code as well. So that generates a coherent set of files that we can manage, update, and change very quickly and very easily. So that saves an awful lot of work and also guarantees that it comes out correct as well. Okay, so that gives us memory protection zone. So as each thread's running its sandbox, it can only access its own resources. But there's still a bit of a further problem in that all of our RTOS objects, like mail queues, event flags, etc., are accessed via pointers rather than addresses. So we could accidentally bypass the memory protection zone. So there's another feature within the functional safety version of RTX, and this allows us to define each thread with a safety class. So basically a safety class is simply a number, and we allocate each thread with a safety class value, and a thread cannot access or modify an RTOS object if it has a higher safety class value. So again, we're restricting what each thread can access. So here, again, this is done through the attributes. So when we, for example, create an event flag, we can program the attribute bits with a specific safety class value. And then when we create that flag, it's created with a specific safety class. If we try to access those event flags with a thread that has a higher safety class value, then it will return an error, and it can no longer proceed. That gives us functional isolation, but now we need temporal isolation. And this is done with thread watchdogs. So when we create our FuSa safety threads, each one has a thread watchdog, and we can software watchdog so that we can guarantee the maximum runtime for that particular thread. So this has to be patted each time we go around the loop within the thread. If it fails, we can decide how we want to manage that temporal failure. So if it's an interference-free component, we could simply stop that thread running and restart it and hope it restarts successfully. If it's a safety-related thread, we can try to take some mitigation, or we can place the application into its fallback mode. But either way, we're monitoring the execution of all of our threads in the code with software watchdogs. If any of them fails their runtime, we can take corrective action. So this is simply done through OS thread feed watchdog. We tell it in milliseconds its timeout period. And then if we're waiting for an event to trigger execution of the thread, we can have a timeout on that. If the thing times out, it goes around the do while loop, pats the watchdog, and then waits for the flag to be set. So as I mentioned, we now have quite a hierarchy of faults within our system, beyond just a basic RTOS fault or a processor exception. So we can consider and take more sophisticated approaches to managing faults within the system, either try to recover the system or put ourselves into a safe operating mode. So these are the additional features that are provided by the functional safety version of RTX. it allows us to create systems where we're separating the interference-free components and the safety components, so we can spend less time on certification and also guarantee execution of our system as well. Well, I hope that's been useful for you this morning. If you have any questions, please either email me directly, or I think at the end, after the questionnaire, you can raise a question on there as well. Thank you very much for your time today, and I think end of this month we'll be doing another webinar, which is an introduction to cryptography for small embedded systems. So again, if that's of interest, I hope to see you then as well. Thank you very much. Goodbye.